I'm continuing my video series on for Psych 611, and this is the last set of lectures on the analysis of variance, and specifically this video, and if there needs to be another one, is going to focus on factorial designs. I think I should be able to cover this set of lecture notes in one video, but we'll see. I don't want to get the videos too long. So this first part really is going to be focused on factorial designs, which introduces the concept of moderated effects or interactions. And what I'm going to describe is how interactions are typically discussed, and then how probably the typical discussion may be misleading, and then how to correctly interpret factorial designs and specifically interactions. So to bring you full circle back to the concept of the general linear model and how the general linear model handles both main effects and interactions, is that we first need to know what this general linear model is. I've gone over it a lot of times in class, so a lot of this is just review. But what it is it's a representation of a prediction model that is based upon a linear, as in additive, model, and the predictors are weighted according to their ability to accurately predict the dependent variable, and these weights are all based upon the concept of least squares. We've discussed this before. And this is the generic general linear model. And then to expand it, we have, for main effects, the general linear model looks like this, where we have two predictors. Now this is a really good analog for regression, but I'll explain to you later that there's no difference. That here we have two predictors, and in this case two covariates, and we have a B1 and a B2, and those are the weights. And then a B naught, which is just a scaling factor, or the intercept, and then error. Now, the concept of main effects are that these pluses are nothing but ors. So it's x1 or x2, or the intercept, or error. Now we can also include a more complex model, as in this one, where we have the main effect of x1, or it's x2, or it's x1 and x2, which is that asterisk is a multiplication. And that multiplication means that we have an idea that we're going to have main effects, so x1 or x2, or that together they work in conjunction to produce an effect that's different than just the main effects. So that's the logic behind when we add in interactions into our model, that they're still additive, but they're additive in the sense that we originally were just using them as either or. So you can have one predictor, or you can have a second predictor, or you can have both. And that part is the interaction. That is the and part of the general linear model. Okay, now in class, I've mentioned this before, one of my favorite interaction models is a model based upon antabuse. And antabuse and alcohol, when they're combined, they produce a rather substantial effect. Substantial in that it's far different than the main effects. So I've manufactured data, and what I want to do is I want to show you an example. So I have a very small sample. There's 12 observations, and I have two fully crossed factors, antabuse and alcohol. Antabuse is binary and alcohol is binary. So within each one of these groups, there's 6 people who don't have antabuse and 6 people who do, and 6 people who take alcohol and 6 people who don't. So you'll notice that there's 1, 2, 3 ones within the no antabuse group for alcohol, and there are 3 zeros. and there's 1, 2, 3 ones of alcohol in the antabuse, and there's 1, 2, 3 zeros. That's no alcohol in the antabuse group. So antabuse and alcohol are fully crossed in this model. And if I run a standard analysis of variance, this is what I get. So what I get from this model is I get both a main effect that is significant. That is that antabuse as a main effect produces a substantial prediction that when you have antabuse versus not having antabuse, that there is a significant difference in having antabuse in terms of the response or the y variable. So this response variable, this dependent variable, is predicted significantly by antabuse as a main effect. Okay, why? Because we have the p-value, right? But there's more to it than that. There's sufficient variability both between the groups, that is, the antabuse group compared to the no antabuse group, in comparison to the noise, the signal over the noise. So the F is the signal over the noise. So if you take 290.08 and you divide it by the noise, 0.83, you'll get a rather large number, 348.10. Similarly, alcohol effects, you'll get the same effect. Then we have antabuse and alcohol multiplied together. Now you'll notice that if you multiply a 0 by anything, right, you get a 0. So this is a 0, this is a 0, these are lots of zeros, and then we'll have 1, 2, 3 ones. So this is really going to be an interesting comparison because there's only 1 degree of freedom because they're binary. Okay, there's just 2 groups in each one. And I'll show you exactly how that comes out. But what I want to do is I want to talk about how the typical interaction is reported. The way it's typically reported is this way. That you have the mean of responses, and what these are the raw means. So down on the x-axis, you'll notice this is antabuse. This is either 0 or 1. They either got antabuse or they didn't. Let me see if I can decrease the, there we go. So this is antabuse 1, no antabuse. Alcohol, if they got alcohol, they have a 1 or a solid line. If they weren't in the alcohol group, then they got a dashed line. So what is this telling us? The interaction is telling us that there is a significant difference in terms of the combination of these 2 variables. Remember, it's alcohol and antabuse. It's the and. And what it's saying is that this effect, the combination of the 2, is substantially different than what we'd expect from either one of these main effects. Now, while this interaction and this typical interaction plot look like a perfectly defensible idea, it's actually wrong. And the reason why it's wrong is that that's not what's being reflected in this F test right here. That this F test reflects a residualized effect. Okay, now I mentioned this in class. And what I want to do is I want to go over exactly what that means. So what does that mean? Well, these are the raw means that I plotted above. So the 0, 0 group got 1.33. The 0, 1 group, so you'll see that this is, these are, I believe, it's rows and columns, so it's antabuse and, it's alcohol and then antabuse. So if you take a look at this, you'll notice that the group means are reflected in this figure right here. This is 1.33, this is 5, and this one is 21. Now, I manufactured this data, and I manufactured it specifically to show a pretty extreme example. But what I've done here is I've calculated the mean response for each one of these things, and then the mean for antabuse and then the mean for alcohol. Okay, now why did I do that? Because really what I want is I want to be able to show you that there are effects that we are calculating. And the effects that we're calculating are residualized effects when we are testing interactions. We have to take out the mean effects of the main effects. So what does that mean? This is the mean response rate for these two groups. But in order to understand what the effect is that we're testing, we have to take the response rate, and then we have to subtract out the mean of antabuse, and then we have to subtract out the mean of alcohol. And when we subtract out both of these from this value, we get -5. Okay? So this is the residual. This is the residual effect. All right? Similarly, if you take 5, that's the mean response for this group, no alcohol, antabuse group. The mean response is 5. If you subtract out 13 and 3.17, you will get -11.17. Okay? So what I'm doing here is I'm walking through how to calculate each one of these columns. So similarly, if you take 5, this is the mean response. These are just the cell means that were calculated up here that I graphed. And what I'm doing is I'm subtracting out the mean effects. Okay? Once I calculate these residuals, then what I want to do is I want to take the residual and I want to eliminate the grand mean of the residuals. So -5, subtracting out the mean of all of these gives me 3.08. Okay? -11.17 of the mean of these things gives me -3.08. Okay? The mean just so happens to be 8.8 or 8.9. So this is obviously it's a rounding a little bit. But what we've got here now is we have residualized effects with none of the mean effect in here. And this residualized with no grand mean is this interaction plot. And this is the correct interaction plot. This is the plot that's actually showing the effect that is being tested. So this is quite dramatically different than the plot that I showed you originally. This shows, if you look at it, yeah, there's a bit of an effect, but this is the real effect that's being tested with the F-test, because the F-test on the interaction is a residualized test. Okay. So, how do we match what's being tested? As I said before, this is the summary of our tested effect. Remember, 290 divided by 0.83 gives us 348.10. Okay? So you'll see here, this is the original ANOVA. Suppose I ran just an ANOVA with the main effects. Okay, what do I get? What do I see that's different? Well, none of these are different except the F-tests are different. And why are they different? Well, because I don't have this effect in here. Okay, so it goes into the residual, which means that I have a lot more noise. So if I put the signal over a new noise term that's a lot larger, my F value goes down. Okay, so this is simultaneous sums of squares. If I omit a relevant variable, I am going to decrease my precision of my estimate because I am leaving perfectly good variance on the table that could be explained. Remember, the F-test is signal to noise. If we have a lot more noise that we haven't accounted for, and we could, and obviously we can because the antabuse by alcohol interaction is significant. It accounts for a substantial amount of variability. Okay, but what we're doing is we're leaving it. So if you take 114, right, If you take 114 and you add 6.67, it's these sums of squares that we're adding up, and you'll get, sure enough, 120.75. And then the mean squares is nothing more than the sums of squares divided by the degrees of freedom. Remember, I told you this before in class. Mean squares are variances, and variances are nothing more than sums of squares divided by degrees of freedom. This is why it's called analysis of variance. So we're leaving variance on the table. And that's not a good thing. Okay, suppose, though, that what I really want to do is just test the interaction. Well, if I test the interaction alone, without testing the main effects, I get a substantially different test than if I tested my interaction and the main effects. Why is that? Because the interaction is a residualized test. It's a residualized test because the main effects have to be taken out. Now, when we plot the raw means, we are essentially plotting this effect. We are plotting as if we tested the interaction as a main effect. So that's not right. That is not right. And you'll notice here that here is a situation where I residualize out the main effects from the interaction, and you'll notice that the F value is identical to the F value that we had originally. Okay? Well, not exactly. Now, why is that? This F value, okay, is based upon the mean squares, not the sums of squares. 14.08, look at right down here, 114.08. But if we look at the degrees of freedom, whoa, wait a second, I've residualized out, but I still have many degrees of freedom, right? Take a look at this. 114.08 divided by 1 is 114.08. But look at what happens when I test my interaction, taking out the main effects. I now have degrees of freedom of 3. So I don't have the same mean squares. I have the same sums of squares, but they're not the same mean squares. And therefore, my F test is substantially lower. Why? Because look at this mean square. Now I'm not dividing 114.08 by 1. I'm dividing it by 3. Okay, so it's almost 40 as opposed to 120-ish. Therefore, the F value still is this signal over noise, but it's substantially smaller, right? Similarly, this is what it looks like. If I've residualized out everything, you'll notice that antabuse and alcohol no longer have main effects, but by including them, look at the degrees of freedom now. And this, again, is the test that we are performing. This is the test we're performing, and what I've been doing is telling you the same point over and over again. And I want to emphasize it, that this interaction is the true interaction that is being tested. So therefore, when you're plotting the interactions, you want to plot what is being tested and not what is not being tested. Okay, to wrap up this and to not extend to another video, I want to talk about a few other important details. First, nested versus crossed effects. When I mentioned before in ANOVA, and I said ANOVA requires independent variables. And so therefore, it requires that all the effects, the main effects for your factors are crossed. When they're nested, what we have is we have confounded designs. And you noticed that before. ANOVA doesn't handle confounded designs very well. It doesn't handle nesting very well. And so therefore, you're better off moving towards something that does not have restrictions on the type of design. Nested effects are those in which the factors, the predictors, are confounded. It's no different than what we talked about in the MRC modules about multicollinearity. Additionally, with ANOVA, I mentioned that balance in the design is really important. The reason why it's important is because of this whole idea of partitioning variance evenly and expecting there to be a homogeneity of variances across cells. If you have unbalanced designs, if you just think about it, think about what it means to be a mean in each one of these cells if each cell has a different number of observations. As the observations increase, we know that the precision of our best guess, the mean, gets better. That's the law of large numbers. But when we have differential precision in each one of our cells, we start introducing noise in all different areas of our model. ANOVA doesn't handle unbalanced designs well. Okay? It's the same with nested and crossed effects. Nesting is a headache. Having imbalance in our designs is a headache. Another headache, but it's more of a cognitive problem than anything else, are multiple interactions, so multi-level interactions. I've just shown you a two-way interaction. There are two main effects that interact, but you can have three-way, four-way, five-way interactions where you have 5, 6 factors all interacting. Why do these n-way interactions pose such a problem? They pose a problem because for every interaction that we expand upon, we have to residualize out the main effects as well as the previous interactions. That's just the way these interactions get tested. So as we get more complicated factorial designs, we have to pay attention to the fact that each one of our interactions that gets more complicated is really a test that is a test that's been fully residualized from all of the effects that preceded it. This is an important point when you're trying to interpret those interactions. Okay, just as I showed you with a two-way interaction, it's way more complicated than just plotting the raw means. Similarly, we have the problem that comes into focus with repeated measures. Now, repeated measures is a similar problem to n-way interactions. When you have repeated measures, we have now more dependent t-tests, right? It's the analog to repeated measures, is that you have a dependency where the same individual supplies data for multiple occasions. Now, when you have repeated measures on an individual, there has to be certain constraints that the data hold to. And this is where we start getting into way more complicated models and interpretation. For example, when we have a repeated measure design, we want to make sure, one, that the measure doesn't change over time. That is, the properties of the measurement don't change. You don't change the actual measurement process, and that the means and standard deviations or expected variability for your measure, regardless of the time point, should be the same. And that just is not true. Okay? It's not true for most of our data. It's not true for most of our models because we intervene. And as our experimental units get better, we can have ceiling effects or floor effects with our measure, and therefore we get differential variance over time. Next is multivariate measures, or MANOVA. So you have not just repeated measures, but you have repeated different measures. Now that's a whole different nightmare. I mentioned in class very quickly that MANOVA is rarely, if ever, indicated in any type of model. Beware if you start reading MANOVAs. Most of us can't interpret them very well because they're just a mess. You get an omnibus test, and with that omnibus MANOVA, you must then start running protected tests. Okay, I told you all of these different euphemisms for protected tests. So protected tests in multivariate analyses of variance are essential, but then they start getting really complicated when you include both repeated measures as well as different measures, and then you have different interactions and potentially different balance problems across your models. These are all complications in the ANOVA model. And then finally, you have kind of what I'm talking about is this idea of split plot designs, where you have both within subject or repeated measures design, as well as between subjects. So you have two groups that are getting repeated measures. Split plot designs are unique in many ways, not to social and behavioral sciences, but unique in the history or the annals of history for statistics, where Sir Ronald Fisher designed studies for farmers. And the idea of a split plot design, the plot literally means it is a plot of land. And the reason why the plot of land is split is because the plot of land has certain attributes of it that you wish to measure. And so you'll have different plots, but then you're going to split the plot according to what type of effect you want to induce on it. Split plot designs introduce complexities to interpreting our models, much like repeated measures, much like ANOVA, and they also introduce both between and within effect potential interactions. Woo! Now we're talking about real complicated designs. So what I want to impress upon you is that for this class, I have only scratched the really, really bare minimum surface of what analysis of variance is. It gets way more complicated, but I think at this point you'll have a much better appreciation for why conceptualizing ANOVA as part of the GLM and then realizing that the GLM can be satisfied by either multiple regression and correlation or analysis of variance, that you get more bang for your buck by understanding multiple regression and correlation than from analysis of variance, mostly because of these things. These are the weaknesses of ANOVA. Okay, that's what I want to finish off this class with. I know that this is complexity, and I've really ramped up the details for this, but it's been a fun semester, and I hope you enjoy this series of lectures. Everyone should be scheduled for the final module, and I look forward to seeing everyone. Bye now.